Hello there, this is a look at constant acceleration equations, often called SUVAT equations. So we're going to look at this for Year 12 A Level Maths. Um, so we've already seen a little bit on this on exercise 20A, but before we get on to that properly, I'm going to ask you to do a few questions of just making sure you're good at conversions. Now, this basically is all reliant on the formula speed equals distance divided by time. It's a GCSE formula. And it really is that easy. Well, it's not quite that easy because in three of them it is. These first three, I want you to work out the speed a car is traveling, 240 miles, 4 hours. And notice the answer I want is in miles per hour. So effectively, the answer I want in miles per hour is in agreement with number of miles and number of hours I give you. And for the first three questions, it's like that. But for D, E, and F, these are the slightly trickier ones, D, E, and F, because I say I'll give you 5 kilometers, but 15 minutes, and yet I want the answer in hours, kilometers per hour. So you're going to have to do some conversions on the last three. So I suggest you pause the video and we'll see how well you get on when I come back. Okay, so pause the video now, please. So look, I've just paused the video. I'm hoping you've done your job as well and you've done these questions. So here are the answers according to me, at least. Hopefully I've got them right. So there they are. So these are the ones, these three here, D, E, and F. If you've got any wrong, I'm going to guess it's those three. So check your answers, please, and then we'll go on to the next part, the video. Now, look, SUVAT equations, constant acceleration equations. We get loads of questions where we are asked about velocity, displacement, time, acceleration, etc. And you can try to do them just by, in your head, a kind of common sense approach. But after a while, they get a bit tricky. And then they can get very tricky. And so we try instead to use a bunch of mathematical equations based on that common sense approach. But we end up trying to use these equations all the way through. And look, first one's displacement. So S is displacement. It's not the obvious letter, is it? I agree. But this is the letter we always use. So you're going to have to get used to the fact that S is going to be used for displacement. U is the initial velocity because we use V for the final velocity. And we need to know the speed at which something is traveling at the start and the speed at which something is traveling at the end. So for that reason, we use U and V. A is a bit more obvious. That's the acceleration. And T is a bit more obvious. That's the time. And so these letters are what we always use. Particularly the S, you're going to have to get used to the fact, as I say, that it's displacement. Now, based on that, we get these equations. And the first one is V equals U plus AT. And you'll notice from these, based on the SUVAT that I wrote before, and I'm going to be writing SUVAT quite a lot, you'll notice that going across there, the obvious one is I'm missing the S. So if S is missing, I use V equals U plus AT. Second equation is S equals a half of U plus VT. That means times by t. And you'll notice the a is not there this time. So every time we do a new equation, one of the letters is missing. And that means if you don't know that piece of information, it doesn't matter. You can still use this equation. Next equation is also in S. S equals ut plus half at squared. And there's some the v is missing. S equals vt. They're very similar, these equations. And interestingly, the physicists amongst you won't have seen this one. They don't tend to teach you this in science. But S equals Vt minus a half at squared. The U this time is missing. And if I'm missing the T, V squared equals U squared plus 2AS. 5 equations used in 5 different situations. And notice these only work if we use what are called SI units, standard international units. So for instance, meters per second or meters per second squared, often written ms to the minus 1 or ms to the minus 2. So these are the kind of things that we expect them to see. If we haven't, we've got to convert them, hence the starter. So here's a question. Particle has initial velocity. So immediately I'm thinking this is a standard SUVAT question. I shall find out properly if it's not in a bit. So I always start off by writing the SUVAT out. And it says the initial velocity is 40. Now remember 40 therefore is u, the initial velocity. It moves in a straight line with constant acceleration. Constant acceleration is 10. Find the velocity, so I want the velocity after 5 seconds. And you straight away realize I haven't got the S. And that sounds to me like V equals U plus AT. That's the equation. Now, look, I know that because I use it so often. So that's the one I'm going to use. But you've got to get better and good at knowing which equation to use. V equals U plus AT then, so I know V equals, no, V is what I want. I nearly did that wrong. V equals 40 plus 10 times 5. 10 times 5 is 50, so V equals 90. Now this is the velocity, so it's meters per second. What have I got? Oh, I've got a lot of working out coming up here. 90 meters per second, though, was my answer. Second question. A particle moves in a straight line with a constant acceleration. So again, I'm going to write, I'll write at the top because I think I might need the space at the bottom in a bit. SUVAT. Notice it says, if its initial velocity is 5, write that in straight away, and the acceleration is negative. Now it actually means it's slowing down, negative 0.5. What's its displacement? So I'll put a question mark next to that one. From the start after 20 seconds. So t equals 20. And notice I haven't got v this time. And this equation then is s equals ut plus half at squared. That's the equation when you haven't got the v. So if I substitute these in, what do I want? I want the s, that's good. It's always good if you want the one you start off with, but it's not always the case. Sometimes you have to rearrange it. S equals u5 times t 20 plus a half of, what was that? It was negative, minus 0.5 times t squared, 20 squared. And I can just type that into my calculator. So S equals, let's do that. So 5 times 20 plus a half times negative 0.5 times 20 squared. Oh, I get exactly 0. I didn't expect that. But there you go. So basically, whatever it's done, it's gone nowhere after 20 seconds. Let's just see if that's right. Yes, that's exactly right. And then I've got this second equation. On another equation, the particle starts from rest. How long does it take to reach a point 7 meters? So I'm going to do this. I'll try and squeeze it in this space here because I suspect that's okay. On another occasion, so I'm writing SUVAT out again. It says it starts from rest. Well, that's often a phrase to mean u equals 0. How long does it take to reach a point 7 meters? 7 meters away if the final velocity is 2. How long implies I want the time. I don't know the acceleration. So if you don't know the acceleration, again, you've got to go through this process of sussing which one it is you've got. And there's the one that says s equals a half of u plus v times t. So in this case, my s is 7 equals a half of 0 plus 2 times t. Well, the good thing about that is that adds up to 2, and times by a half is 1. So I actually think t is equal to 7 because that cancels with that. 7 seconds. Let's see what I've got. 7 seconds is what I've got, and I've got to use the same equation. So this is what we need to do. Example. A particle then travels in a straight line with a constant acceleration. Constant acceleration is the bit that tells me to use SUVAT. So let's write SUVAT. Its initial velocity is 10, that's u. And after 40 seconds, t equals 40, its velocity is 15. And look at this, I want the acceleration for part A, and I want the displacement after, oh no, that's after 40 seconds. Okay, so, oh no, that's what they said in the question as well. So I, in due course, will want both of these things. But initially, I want the magnitude of the acceleration. Magnitude, by the way, is the posh way of saying the size. How big is the acceleration? That's all that means. So I want the acceleration. Look at that. V equals u plus at. That's the same equation as we saw before. V equals u plus at. This time, look, 15 equals 10 plus a times t, which is 40. And this is a classic example where you have to rearrange. So that 10 can move over to the other side, becomes minus, therefore I've got 5 equals 40a. A therefore is 5 divided by 40. And you're probably already realizing if you're not very good at rearranging equations, this is going to be hard. I get 0.125 in my head when I'm just doing that. And then part B, so that was part A, wasn't it? Part B says, now we don't care about the acceleration. I care about the S. So that sounds to me like S. Yes, so it's S equals a half of U plus V times T again. And you just got to get your head around what you're doing. So S is what I want. That's all. I always prefer that. U plus V, that's 10 plus 15. And you could have just written 25 there, wouldn't be the problem. Times T is 40. So it's a half times 25 times 40. I think that's 500, but I'll do it on the calculator. 0.5 times 25 times 40 is 500. So 500 meters. See what the answers are. Perfect, perfect. Now look, it says some examples lead to a quadratic equation to find time, and these are the slightly trickier ones. So let's have a look at it. Yeah. So it says a bird starts to fly with an initial velocity of 2 meters per second. So I'm going to. It says it should really say constant acceleration, but I'm going to assume it means it. SUVAT I've written out. But it starts to fly with an initial velocity of 2 and it accelerates with an acceleration of 0.3. How long, so I want the time, will it take to fly 100 meters? Oh, that's that one there. Yes, the distance traveled, if you like, displacement. So I haven't got the V, so this equation is S equals UT plus a half AT squared. And as this is what was the prediction up here of what it was going to be. S, of course, is 100 equals U, what's U, 2. And I don't know T, so I have to write 2T plus a half times 0.3. And this is why we've got a quadratic equation. You can see we've got T's in two places, one of which is a squared. So I'll just tidy up this equation. 100 equals 2T plus, I reckon, 0.15 T squared. Now, since it's a quadratic equation, I'm going to use my quadratic equation solver, my calculator. 0.15 T squared plus 2T. And when you do that, you need to move everything onto one side. So minus 100 equals 0. And I need to get my class whiz out. That's probably the Casio class whiz does this very well. And we can go into the menu A button and find the solutions. So if you press menu A on your calculator, and then say you want a polynomial, degree 2, and enter your value. So A is here, obviously equal to 0.15, B is equal to 2, and C is equal to negative 100. And if you ask it what the solutions are, what do you get? So I get, well, it says X, but my X1, or therefore my T values, are negative 33.3 and T equals 20. Now, obviously, this one's impossible. I can't have a negative time that the bird's flying for, so therefore my T is 20 seconds. And T equals 20 seconds is right. Now, notice that was a quadratic equation. Now, you get a variety of examples that in the old days, before we had calculators, were a pain because you had to do solve a quadratic equation to solve all this problem. But now it's just a case of typing into your calculator and it does it brilliantly for you. So, okay then, so that's the end of that. So we'll do perhaps an example to start with in lesson. But other than that, exercise 20B is what we need to do in class. So thank you very much.